Hey guys, here are your notes on section 4.3, the real zeros of a polynomial function, day 1. I just want you guys to understand that chapter 4 is all about working with these higher degree polynomials. Well, remember, the higher the degree gets, the harder or more complicated it's going to become to break these polynomials down and to find their zeros and x-intercepts. So to set this equation equal to 0 and factor it or break it down and find its zeros, it's going to become more and more complicated the higher that degree gets. So in the next couple sections, they try to teach you little hints and tricks and theorems that you can use to help you break these polynomials down and to help you find their zeros and x-intercepts, okay? All right, so let's review. If, let's say, R is a real zero, so it's a real zero, not an imaginary one, not a complex one, it's a real zero of the polynomial function f of x. Well, then what can we say about R? Well, then f of r, if you plug r into that polynomial function, it's going to make it equal 0. That's why we call him a zero of that polynomial, all right? R is then going to be a what of its graph? Well, if it's a 0, that means it's a x-intercept of its graph. Now remember, only the real zeros can be called x-intercepts. Any imaginary zeros are not going to be x-intercepts. They just are zeros, numbers that make the equation equal to 0, okay? Blank is then a factor of f of x. Well, if r is a 0, then at some point we could have written him as a factor x minus r that we would have set equal to 0 and solved for x, and we would have gotten r as our answer, right? And then blank is a solution to the equation f of x equals 0. Well, that's r. R is a solution to that, right? R is going to make that function equal 0. So all of those statements become equivalent once you know r is a real zero of the polynomial function f of x, okay? All right, well, when we start finding x-intercepts and zeros, it's going to be harder when this degree gets higher and higher. So we have to remember what we know about something being a factor. All right, what are factors and division, and what role are they going to play? Well, think about it. What does it mean to be a factor? What are factors of 24? If I asked you that, right? If I asked you what are factors of 24? Well, factors of 24 would be 1 and 24, 2 and 12, 3 and 8, and 4 and 6, right? Why are these factors of 24? What do these pairs of numbers do? They multiply to 24, right? These are pieces that multiply to a product. All right, so those are what we call factors of 24. But that's what they do as pairs. These are numbers that multiply to 24. There's another definition of what it means to be a factor. What individually do these factors do? What do all of these numbers do to 24 individually? They divide evenly in. A factor will divide evenly in to that product, right? And then we can use that as a way to find out if something is a factor. If it divides evenly in and we get a remainder of 0, then we know that number is a factor of 24, right? Okay, so let's see. It says, is 8 a factor of 128? Well, to find out if 8 is a factor of 128, I could sit here and try to think of a pair, 8 and what multiply to 128, or I could test to see if it divides evenly in. If I can divide evenly in and get a remainder of 0, then I would know 8 is a factor. So let's see if 8 will divide evenly into 128 using good old long division. All right, refresh our memory. All right, so how many times can 8 go into 1? It can. How many times can 8 go into 12? 1 time, right? So then 1 times 8, is 8. Then we subtract to see what's left over. 12 minus 8 is 4. We bring down the 8 and we do it all over again. How many times can 8 go into 48? 6 times. Then we multiply. 6 times 8 is 48. We subtract. There's nothing left over and there's nothing to bring down. So that means that 8 just divided evenly in to 128, right? It means that 8 times your answer, 16, will get you back to 128. And I don't have to add any remainder in because the remainder was 0. So that means that 8 is a factor of 128. Okay? All right. Well, what if they wanted to know, is 4 a factor of 78? Well, we could see if 4 and a number multiply to 78, or even quicker, let's just see if 4 divides evenly in to 78. So let's see. Does 4 divide evenly in to 78, okay? Well, how many times can 4 go into 7 without going over? one time. And then we multiply. 1 times 4 is 4. We subtract to see what's left over. It's a 3. Bring down the 8, and we do it all over again. How many times can 4 go into 38? Well, it can go in 9 times without going over. All right, 9 times 4 is 36. Subtract to see what's left over. We have 2 left over, nothing left to bring down, which means 2 is our remainder, which means that 4 did not divide evenly into 78. You had left over. You couldn't get it to multiply, or I'm sorry, divide evenly in. All right, so the way we could write this is the answer is no, it's not a factor. All right, and the way to show it is we would have to take 4, what we divided by, times 19, our answer, and then we'd have to add in our remainder of 2 in order to get back to the 78, what we were dividing into, right? 4 times 19 is 76, plus the 2 left over, that gets back to our 78. But if you remember when you were long dividing polynomials in Algebra 2 last year, a lot of times they want the remainder to be written as part of the answer, as part of one expression. So we can't just say, oh, well then 4 times 19, our answer, plus 2 left over will get us back to 78, right? Because that's going to be 21, and 21 times 4 is 84. So you can't write it like that. But a lot of times they want that remainder to be written as part of the answer expression. So if you remember, you kind of had to write it kind of weird. It would be 4, what you divided by, times 19, plus the remainder of 2 over what you divided by 4. And that's how you get the remainder to be written as part of that one expression. Because now when you multiply it back in, 4 times 19 is 76. 4 times 2 over 4, the 4s will cancel and just leave you with the plus 2. And that's how you get back to the 78. So do you guys remember when you were dividing polynomials, if you had like a remainder of 2 and you divided by x minus 1, they made you write the 2 over the x minus 1. They made you write that remainder over what you divided by. Well, that's why. That's the only way to get the remainder to be written as part of the answer as one expression. Again, I just tend to write it like this: 4 times 19 individually plus the remainder by itself. But if you want the answer and the remainder to be written as one expression, then you have to put the remainder over what you divided by. And that's the only way it'll multiply back to what you were originally multiplying to. I just want to go over that because sometimes people forget that there's a weird way to write the remainder when you're dividing polynomials, which is what we're going to be working with, right? I wanted you guys to see it with numbers first, but we're going to be dealing with polynomials, right? Is x minus 1 a factor of another polynomial? So we're going to have to look at it like that, all right? So I just wanted to review that with you guys. Okay, all right, so it's pretty safe to say that a very key way to tell if something is a factor of something else is to see if it divides evenly in, to see if that remainder is 0. If you can prove the remainder is 0, then you can prove something is a factor. If you can prove the remainder is not 0, then you can prove something is not a factor. So what the remainder theorem is going to do for us in this section, the remainder theorem is going to offer you another way to find the remainder without having to go through the division process. That's the only purpose of the remainder theorem. He's just giving you another way to find the remainder without having to use division. Okay? All right, so let's see what it says. The remainder theorem says, if a polynomial function f of x is divided by a polynomial of the form x minus c, and again, it has to be in this linear form, x minus some number. So either x minus 2 or x plus 3. Again, that's fine if it's plus. It's got to be in this form, though, this linear form. So it says, if a polynomial function f of x is divided by a polynomial of this form, then f of c is going to equal the remainder. So you'll be able to find the remainder without doing division. You'll be able to take this, whatever you're dividing by, x minus c. Now again, c is not just, oh, pick your favorite number. It comes from what you're dividing by. If you are dividing by something of this form, x minus c, then what you would do is take x minus c, set it equal to 0, and solve for x. And then x would equal c. So c is going to be this magic number that if you plug it into the actual function, the number the function will spit out when you plug c in is the remainder. That's what the remainder theorem is saying. If you take this magic number from this piece that you are dividing by and plug it into the function itself, then the number the function spits out is the remainder. So it's not like you can just plug any number you want into this function and the remainder will come out. No, you have to plug this c value into the function in order for the remainder to be what comes out. So it's a good thing to do. So instead of you having to take this and divide it into the polynomial to see what the remainder is, you can just take this magic number, plug it into the remainder, and see what number comes out. Okay, well, why does the remainder theorem work? Well, look at what it's saying. It's saying that when you plug this magic c number in, the remainder will come out. And that's going to happen when you take f of x and divide it by something of this form, x minus c. So guys, it's saying that if you take f of x and you divide it by x minus c, right, you're going to get some answer. You're going to get some answer, some quotient polynomial, let's call it q of x, and then maybe plus some remainder, right? Okay, so if I take some polynomial function f of x and divide it by a polynomial of the form x minus c, I'm going to get some polynomial as my answer, maybe plus some remainder. Well, the remainder theorem is saying if you plug this c into that function, it is the remainder that will come out. Why? Okay, well, let's rewrite this. All right, so if f of x is divided by x minus c, right? Well, then how many times can x minus c go into f of x, right? That's what we're doing. And we're going to get some quotient polynomial as our answer, and then probably plus some remainder if there was a remainder. Okay, well, let's put this back together. According to what I took up here, if I took 4 and times it with my answer and added in the remainder, it should get me back to what I was dividing into, right? So if I take x minus c, what I divided by, and I times it with my answer, this answer polynomial, this quotient polynomial that I get, right? And then maybe I have to add in some remainder, it's going to equal, it's going to get me back to the original polynomial I was dividing into, okay? So let me just rewrite this. So f of x, what we were dividing into, is always going to be equal to what we divided by times our answer, our quotient polynomial, and then plus the remainder. So the remainder theorem says that if I plug c into this function, it's the remainder who will come out. So watch this. If I plug c in, it's going to be f of c equals, c goes in for x, so c minus c, times the quotient of plugging c in, and then plus the remainder, right? Well, what's c minus c? C minus c is 0 times q of c, and then plus the remainder. Well, 0 times q of c is 0, and then plus the remainder. 0 plus the remainder is the remainder. So f of c, no matter what polynomial it is, when you plug c into this polynomial, it is the remainder that the function will spit out, okay? So again, all the remainder theorem is doing is giving you another way to find the remainder. So instead of you having to sit there and divide the polynomials together, you can just see, well, hey, if I plug c in, what number comes out? It will represent the remainder. So if 0 comes out, you know the remainder was 0 and it divided evenly in. If 0 doesn't come out when you plug this c in, then you know the remainder was not 0, and this is not a factor of this polynomial. It did not divide evenly in. Okay, so that's the only thing the remainder theorem is doing. It's giving you another option as to how you can find the remainder. All right, so let's use it. Okay, so using the remainder theorem, it says find the remainder if f of x, which is equal to this polynomial, is divided by x plus 3. Well, guys, instead of us sitting here to find the remainder and dividing x plus 3 into this polynomial, we're just going to use the remainder theorem. So take what you're dividing by, this x plus 3, that's your x minus c, if you will. So take x plus 3, set it equal to 0, and let's find out what that magic number is. It's going to be negative 3. So think of negative 3 as this c value. So according to remainder theorem, the remainder theorem says that if I plug negative 3 into f, it's going to equal the remainder. All right, so let's plug f of negative 3 in and see what comes out. So f of negative 3 is equal to negative 3 goes into the third power minus 4 times negative 3 squared, and then minus 5. I would type that right into your calculator, and what you get is negative 68. So when negative 3 went into function f, a negative 68 came out. So guys, clearly a 0 did not come out of this function, which means it's not a factor. It did not divide evenly in because the remainder was not 0. If the remainder was 0, then 0 would have come out when I plugged negative 3 in. So that means x plus 3 does not divide evenly into this polynomial, and it means x plus 3 is not one of his factors. All right, so that's no. So that means the remainder is negative 68, which is really what they asked us to find. They just asked us to find the remainder. Now, guys, let me show you this in case you guys remember this. You could have found the remainder by doing division, long division, or synthetic division. So do you guys remember synthetic division? It was the shortcut to long division when you were dividing by a factor of something like x plus 3. So you would take all the coefficients, 1, negative 4, we're missing an x term, so we would say there are 0 x's, and then minus 5. So you would take 1, negative 4, 0, and negative 5, right? You would take the coefficients, and then you would use that magic number, negative 3, and this was a shortcut to long division. You would bring that first coefficient down, and you would do a multiply-add process all the way to the end. So 1 times negative 3 is negative 3. Then we add. That's negative 7. Negative 7 times negative 3 is 21. We add it. 0 plus 21 is 21. 21 times negative 3 is negative 63. And then we would add negative 5 and negative 63 is negative 68. And then you would circle that last number because that last number represents your remainder for the synthetic division process. So it is true. We are getting a remainder of negative 68, whether I did it by dividing or whether I used the remainder theorem. So again, the remainder theorem is just giving you another option as to how you can find the remainder without using division. All right, so again, we know the remainder and we know that x plus 3 is now no longer a factor. All right, so it says in example 2, find the remainder if f of x is equal to this polynomial is divided by x minus 1. So again, they just want to know what's the remainder. So guys, technically we're supposed to fill in zeros, right, for all of the missing terms. This is a degree 100 polynomial. You'd have to fill in a lot of zeros to get down to that 0x, starting from a degree 99x. So you wouldn't want to fill all those zeros in, so I don't want to have to go through this synthetic division process to find the remainder. I'll just use the remainder theorem to find my remainder. All right, so we take x minus 1. We set it equal to 0. We find out x equals 1. So 1 is our magic number, right? So the remainder theorem says that if I plug 1 into this polynomial, it is the remainder that will come out. So let's see what we get. Let's plug f of 1. Let's plug 1 into function f. So that's going to be 1 to the 100th power minus 4 times 1 to the 99th power, and then plus 3. Right? We could plug this into our calculator. This is pretty easy. 1 to the 100 is 1. 1 to the 99 is 1. 1 times negative 4 is negative 4. And then bring down plus 3. I'm going to get negative 3 plus 3, and it's 0. So f of 1 equals 0. So that means the number that came out when I plugged 1 in, this magic number, was 0. So the remainder is 0. Okay, which means x minus 1 does divide evenly into this polynomial, and x minus 1 is one of his factors if I was trying to break him down into factors. All right, so that is what we know. We know the remainder theorem lets us find the remainder by plugging this magic number in. Okay. All right. Well, what does the factor theorem says? Again, the factor theorem is pretty self-explanatory and pretty obvious. The factor theorem says let f be a polynomial function. All right, x minus c is a factor of that function if and only if f of c equals, well, what does the remainder have to be when I plug this magic number in order for it to be a factor? F of c has to equal 0. The remainder must equal 0 in order for something to become a factor. It has to divide evenly in order to be called a factor. All right, so the factor theorem just says that your remainder better be 0. F of c better equal 0 in order to call x minus c a factor. Okay? All right, let's use the factor theorem, which again, the factor theorem is just going to be, is the remainder 0 or not? So you still have to use the remainder theorem to apply the factor theorem. All right, so it says use the factor theorem to determine if x minus 1 is a factor of this polynomial. Well, again, if we want to know if this is a factor of that, I need to know the remainder. So you can either divide it in using long division, you can divide it in using synthetic division like up here, or you can just see what number comes out when you plug that magic number in. Is it 0? We can use the remainder theorem. All right, so I think I'll do that. So x minus 1 equals 0, x equals 1. So therefore, f of 1 is going to equal my remainder. So let's see what it is. So let's plug 1 in and let's see if I get 0 out. Because if I get 0 out, then I'll know it's a factor. I'll know the remainder is 0. All right, so it's going to be 2 times 1 to the third minus 1 squared plus 2 times 1, and then minus 3. All right, 1 to the third is 1. 1 times 2 is 2. Minus 1 squared is 1. Plus 2 times 1 is 2. And then minus 3. From the left, 2 minus 1 is 1. 1 plus 2 is 3. And then 3 minus 3 is 0. So 0 does come out when I plug 1 in. So that means the remainder equals 0. So that means x minus 1 is a factor of that polynomial. If I was going to break him up into factors, x minus 1 would be one of them, okay? All right, so we know the remainder is 0. We know x minus 1 is a factor. All right, let's look at example 4. Since we just found out that x minus 1 is a factor of the above polynomial function f of x in example 3, they want you to write f of x in factored form. Okay, well, think about it. One of the ways we would try to factor this is probably factor by grouping, right? It's 4 terms, but it doesn't factor by grouping. So it's kind of like, wait a minute, how do I factor it if it doesn't factor by grouping, and I don't know how other techniques to factor a degree 3 polynomial? Well, now that you know x minus 1 is a factor, what do you know x minus 1 will do to this polynomial? What do factors do? They divide evenly in. So I can actually take that division step now, and I can divide this polynomial into that one, and I will be left with an answer polynomial that is of a smaller degree, and I can start breaking it down that way. So I know x minus 1 will divide evenly into that polynomial. So I can use that to help me factor it, to write it in factored form. So I'm going to actually do the division process now. Now that I know it'll divide evenly in, now I know it's worth dividing. So let's divide it in. You can either divide this in long division, or you can divide this in using synthetic. I'm going to do synthetic. So I'm going to take this x minus 1, set it equal to 0, x equals 1, right? So that's my magic synthetic number as well as that magic plug-in number. All right, now I'm going to gather my coefficients, right? I have a degree 3, a degree 2, a degree 1, and then a just number. So I'm not missing any terms, so I don't have to fill in any 0 coefficients. So I'm going to start with my coefficient of 2, and then my coefficient of negative 1, my coefficient of 2, and my coefficient of negative 3, and I'm going to be able to use synthetic. Now again, I know my remainder is 0, so I better get a 0 as my last number. All right, bring the first coefficient down, and we start that multiply and adding process. 2 times 1, 2. Add is 1. 1 times 1 is 1. We add, we get 3. 3 times 1 is 3. We add and we get 0, thank God, because we said we had to, because that is the remainder. So now to write this in factored form, well, again, 1 started as a factor of x minus 1. So he's going to be x minus 1 as a factor. And then remember, after you do your division, these become the coefficients to a polynomial that is 1 degree less than the original. Because if I take a linear degree 1 polynomial and divide it into a degree 3 polynomial, my answer will be a degree 2, 1 degree less than the original polynomial. So this is going to be the coefficient to a 2x squared term, plus that's the coefficient to a 1x term, and then that becomes a just number, right? X squared, x to the first, and then no x's. And now I've written this in factored form. This will multiply back to the original polynomial. These are pieces that multiply to that polynomial. So now I know in factored form, it looks like x minus 1, and then times 2x squared plus x plus 3. Now again, that's a quadratic. So normally what we would do is try to factor it again because we know how to factor quadratics. They're our babies, right? What times what gets me 2x squared? That's a 2x and a 1x. And then what will multiply to 3 and then add up to 1x? Well, unfortunately, nothing does. So this quadratic does not factor again. So I'm not able to factor it again. I'm just able to leave it as these two factors. So this is that polynomial in factored form. Okay, so again, you can use your synthetic to break this degree 3 polynomial down into a degree 1 and a degree 2 polynomial. So these are tricks that we're going to use. We can use things that we know are factors to divide into these higher degree polynomials to start breaking them down into smaller degree polynomials. And that's how we'll be able to find more x-intercepts and more zeros. Okay. Well, just to remind you guys, we've talked about this before, because we're going to be trying to break down all of these bigger, higher degree polynomials, the more tricks and tips we know, the better. So remember, the fundamental theorem of algebra is a theorem that says a polynomial function of degree n has at most n zeros, okay? So if it's a degree 4 polynomial, then it can have at most 4 zeros, all right? That's important. So you kind of look at a degree as like your cheat sheet. If it's a degree 4, you know you're looking for 4 zeros. If it's a degree 3, you know you're looking for 3 zeros and so on. And you can't have any more than that. All right, the real zero theorem says a polynomial function cannot have more zeros than its degree. So for example, a degree 4 polynomial cannot have 5 zeros because remember, each one of those zeros can be written as a factor. And if you have 5 zeros becoming 5 factors, then they're going to multiply out these 5 factors to a degree 5 polynomial. But we knew it was only a degree 4. So you can't have more zeros than the degree. Otherwise, you would end up with all of these factors that multiply out to a higher degree than what the original polynomial was. All right, so you'll never have more zeros than the degree of the polynomial itself. Okay. And I always do that. I'm always looking at what the degree is to kind of remind me how many zeros I should have. All right, last. I know this video is getting long. This is the last thing we're going to do today, and it's kind of why I wanted to make a video to make sure I got all of this in for you guys. One of the last tips they're going to give you is Descartes' rule of signs. And I'm not saying this is something that you guys are going to use every single time because sometimes it's just more time consuming. It's just, again, another thing that if you're ever in a jam and you're trying to figure out what the other zeros could be, this is something you could turn to, all right? So Descartes' rule of signs helps us determine the number of positive and the number of negative real zeros to a polynomial function by counting the number of variations in the signs of the coefficients of f of x and f of the opposite of x, okay? So again, what Descartes' rule of signs is going to do is if you have a degree 5 polynomial, then it's going to help you figure out of those 5 possible zeros, how many of them are positive real zeros and how many of them are negative real zeros, just to kind of give you maybe a position on the graph that they're going to lie in, just kind of help you position the graph better. Okay, so let's see what it says. So according to Descartes' rule of signs, the number of positive real zeros of f either equals the number of sign variations in the non-zero coefficients of f of x, the original polynomial, or else equals that number less an even integer. Now that's kind of confusing again. So all you're going to be doing is to find out the number of positive real zeros. You're going to take the original polynomial function. You're going to count the number of sign changes in the coefficients from left to right. It's either going to equal that number of sign changes or it equals less an even integer. So all that means is you're just going to keep subtracting 2, which is an even integer, until you get a negative number. All right. And again, it sounds complicated. It's actually very simple to do. All right. Now, according to Descartes' rule of signs, the number of negative real zeros of f either equals the number of real zero of f equals the number of sign variations in the non-zero coefficients of f of the opposite of x, or else equals that number less an even integer, which again just means you're going to keep subtracting 2 until you get to a negative number. Okay, so watch. You're just going to count the number of times the coefficient changes signs from left to right. Okay, so again, to use Descartes' rule of signs, you're either going to use the function f of x, the original polynomial, or f of the opposite of x, and you're just going to count the number of times the coefficient changes signs from positive to negative or negative to positive from left to right. All right, so guys, for example, here is a degree 7 polynomial function. So if it's degree 7, it can have at most 7 real zeros. At most 7. There will not be more than 7 zeros. So out of those 7 real zeros, how many stand a chance to be positive numbers and how many stand a chance to be negative numbers? Okay, that's what Descartes is going to help us. It's going to help us determine how many of these 7 are positive numbers, how many are negative numbers. All right, so to determine the number of positive real zeros. All right, so positive real zeros. We are going to count the number of times the coefficients change sign from negative to positive or positive to negative. All right, so the first coefficient is negative. The next coefficient is positive, right? So that's a sign change. So it went from a negative coefficient to a positive coefficient. So that's one time. Okay, now it's a positive coefficient. The next one is a positive coefficient. So the signs didn't change. So we're not going to count that as a sign change. It's positive. Now it's negative. So that's the second time that the coefficients have changed signs. All right, it's negative, and now it's negative. All right, so that didn't change sign. Negative to negative. It did not change signs. So that means the number of times the coefficient changes signs was twice. So that means the number of real zeros is going to equal 2 positive real zeros, or take this number 2 and start subtracting 2 from it. So 2 subtract 2 equals 0. All right, so we know there's going to be 2 positive real zeros or 0 positive real zeros. Okay, take that number, 0, subtract 2 from it. I get negative 2, right? You just keep subtracting 2. Well, I got a negative number, so now I know to stop. So that means out of these 7, either 2 of them will be a positive real zero or 0 of them will be positive real zeros. So the answer is 2 or 0 positive real zeros. Okay, according to Descartes' rule of signs, out of those 7 possible real zeros, either 2 of them will be positive or none of them will be positive. Now, in order to count 0 as an answer, you have to land on it in this subtraction. Okay, all right, well, what about the number of negative real zeros? Okay, well, the number of negative real zeros, you have to look at the function f of the opposite of x. So if I plug the opposite of x into this function, what does the new function look like? And then it's those coefficients that you count the number of sign changes to. So first you have to find f of the opposite of x. So you have to plug the opposite of x into this original function. So negative 3 times the opposite of x to the 7th power plus 4 times the opposite of x to the 4th plus 3 times the opposite of x squared minus 2 times the opposite of x and then minus 1. All right, well, the opposite of x to the 7th power would stay the opposite, and then times it by a negative, it's going to be positive 3 out in front now. All right, the opposite of x to the 4th would go back to being a positive, and then times a positive stays positive 4. All right, the opposite of x squared would go back to being a positive, and then times a positive would stay 3x squared. The opposite of x times negative 2 would now be positive 2x, and then minus 1 stays the same. So guys, I hope you realize that when you plug the opposite of x in, the odd degrees become the opposite. The coefficient becomes the opposite now. The even degrees coefficient stay the same, right? Even degree coefficient stay the same. Odd degrees, the coefficient is now the opposite. All right, so now let's count the number of sign changes in this polynomial. So this is positive to positive, no change. Positive to positive, no change. Positive to positive, no change. Positive to negative, that's one sign change. All right, so the negative real zeros, okay, well, that was one sign change. So it'll be 1 negative real zero, or take that 1 and start subtracting 2 from it. Minus 2 equals negative 1. I got a negative number already. So that just means that there will be 1 negative real zero for sure. Out of those 7, one of them is going to be a negative real zero. All right, and again, I can't say 0 this time because I didn't land on 0 when I was subtracting 2. Okay, and that's what Descartes does. It just takes the number of variations in the signs of the coefficients, and it can predict how many times the sign, how many of those zeros will be positive or negative real zeros. All right, so this 7 out of those 7, 2 or 0 will be positive. One of them will be negative. Well, what about the rest? You say? Well, then the rest stand a chance to be not real. They could be imaginary zeros out of the rest of the possible ones. Okay. All right, let's try it again. All right, one more time. All right, so using the number of real zeros theorem and the Descartes rule of signs, discuss the real zeros of this polynomial. Well, it's a degree 7, guys, right? So if it's a degree 7, we know again that they has a possible to have 7 real zeros. Out of those 7 possible real zeros, how many of them could be positive and how many of them could be negative? Let's do the positive ones first because that's just the same original function. Let's count the number of times the coefficients change sign. So that's positive to negative, that's once. Negative to positive, that's a second sign change. Positive to positive, nope. Positive to negative, that's a third sign change. Negative to negative, no. So that means there are 3 sign changes in the original function's coefficients. So that means the number of positive real zeros, all right, it's going to equal 3 because there are 3 sign changes, or take 3, subtract 2, and you get 1. Or 1. All right, take 1 and subtract 2. I get negative 1. Nope, I landed on a negative number. So that means you either have 3 or 1 positive real zeros. Okay, what about the number of negative real zeros? Well, first we have to find the function f of the opposite of x. So remember, if you plug the opposite of x in, it's going to make all of the odd degrees coefficient change to the opposite sign, and all of the even degree coefficients stay the same. So odd degree, his coefficient would go the opposite. All right, even degree, his coefficient would stay the same. All right, odd degree, his coefficient would go to the opposite. All right, even degree, his coefficient would stay the same. All right, odd degree, it's degree 1, which is odd, so his coefficient would go to the opposite, and then your just number stays the same. All right, now let's count the number of sign changes in f of the opposite of x. All right, so negative to negative, nope. Negative to negative, nope. Negative to positive, that's one sign change. All right, positive to positive, nope. Positive to negative, that's our second sign change. So the number of negative real zeros is going to equal 2. There were 2 sign changes. Or take 2, subtract 2 from it, I get 0, so or none. All right, take 0, subtract 2, I get negative 2, which is a negative number, so stop. So there will either be 2 negative real zeros or no negative real zeros in the 7 possible real zeros of this polynomial function. Now again, I'm not sure how many of you are going to use Descartes' rule of signs in the future when you're stuck. But again, when we're working with these higher degree polynomials, every little tip and trick can help us sometimes when we're trying to break them down. All right, so to establish how many of them are positive or negative, it could help in the future. Okay? All right, so that's where I'm going to stop. I know it was a lot of information. And I think Descartes is the only new information being thrown at you. The zeros and the factor theorems, that should not be anything new. As always, please reach out to me if you have any questions.